Okay. Before the break, before the exam, we already covered unconstrained optimization. Starting from today, we're going to talk about constrained optimization. So let me remind you what is the standard format of constrained optimization. Okay? This is the standard format. This is your design variable. It's a vector, so this is multiple variable problem. Okay? This is your objective function. This means subject to. Subject to means limited by. Okay? And these two are called the constraint functions. Okay? And this one is called the inequality constraint. And this one is called equality. So because here this is smaller than or equals to, so inequality 不等式, and this is equality, equals to, only equals to, so it's called equality constraint. Okay? How about sometimes when you do optimization, you have so-called the variable bounds. For example, this is called the variable bounds. This is the lower bound, and this is the upper bound. Right? Why didn't I talk about variable bounds? Because they are also a kind of inequality constraints. You can rewrite the variable bounds into the following form. You can write, write this as and the other one. So over here, x1 lower bar and x1 upper bar, they are just constant numbers, constants. Only the x1 is variable, right? So they are considered as two of the inequality constraints. So that's why in the standard form, this is a standard form. You don't need to cover variable bounds. This is general enough. Variable bounds are just a kind of inequality constraints. So do you have to design within a variable bound? Maybe yes, maybe not. It depends on the designer. For example, if you are designing a piece of this plate as the desk, you're designing the thickness. So let's say the thickness is your design variable. Thickness cannot be negative. And so you can set up lower bound as 0. So x1 could be the thickness. So x1 must be larger than 0. If you set up this variable bound, during the optimization process, your solver is not supposed to find a variable of thickness that is negative. The optimization process has to stay within this feasible space. Feasible space. So let me remind you another terminology. Feasible versus infeasible. So feasible means satisfying all constraints. And infeasible means violating one or more constraints. So if you violate one of the constraints, then that design point is infeasible. You have to satisfy all the constraints. Then that's a feasible point. Okay? So when you are designing the thickness of the plate, the lower bound has to be 0 or even higher value. Because if you design a plate with 0 thickness, that means no design. And maybe the thinnest plate that you can manufacture is 2 millimeter. So your X1 lower bar can be 2 millimeter because you cannot make 1 millimeter thick plate. Maybe in your company, 1 millimeter plate is too thin, too difficult to manufacture. So as a designer, you decide your lower bar, your upper bar, or you can set it free. You can allow X1 to be any real number. Depends on the problem. Okay? So in order to solve constraint optimization, you need different ways to solve it. Earlier, we talked about Newton's method, conjugate gradient, steepest descent. They are gradient-based approach. They cannot handle constraints. In the solution process, we never talk about constraints because those methods didn't have the ability to handle constraints. At least right now, they don't. Later on, I can show you how you can use gradient-based approach to solve constraint optimization, but that's for later. Let's talk about the simplest method for constraint optimization. So the method I'm going to introduce today is called linear programming. For short, LP. Okay? So when you try to use linear programming to solve the constraint optimization problem, you need to follow a general format for LP. Otherwise, LP cannot handle it. So there is also a general problem format or problem formulation for LP. Okay, the general formulation is minimize C x subject to a. I will tell you more about what are C, A, and small b. Okay, so this is a general format, but let me expand the formulation so that you understand what's going on. So right here, this is C1 x1 plus C2 x2 da 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 Cn xn. Okay, and here we can write this as should be m. Okay, a1 1 a1 2 da 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 a1n a2 1 a2 2 a2n am1 am2. I would like to use small case n. Small case. Okay, so small case. Just to prevent confusion, I should make this one maybe like longer, so you won't be confused. Okay, because right here, this is n rows, and this is n columns, right? So this is m by n, and here, oh, typo, this should be x. So the vector of x, this is n by 1. And when you multiply them together, this at the end is m by 1, right? And besides these setup, there are also some rules that you must satisfy. All the x must be positive, and all the b must be positive. Okay, so the standard format, I can, to save some space. The standard format is right here. In a vector form. And for the rest, they are just vector and matrix. Okay, so over here you can see x vector must be larger than or equals to 0. B vector must be larger than or equals to 0. These two are the only inequality constraints in the standard format. And the rest will be equality constraints. But how about solving a problem with some inequality constraints that doesn't look like these? How do you put them into the standard format of LP? So that will be the next question. So let me give you one example. So how about 3x1 plus 2x2 must be smaller than 3. There is no way for you to put this into your general LP formulation, right? Because of the smaller than or equals to sign. That sign is not equal sign. So how do you put it into the general format? So let me introduce one approach. So if you do this, if you put your actually no. If you say plus S1 and change this to equals, and this is 3. How about adding a new variable on the left hand side and convert smaller than or equals to equals? How about doing so? But when you do that, S1 has to be positive or 0. Okay? So S is called slack variable. Okay? It's called slack variable. So it's actually a new variable, artificial variable that has been introduced to the problem. It's an additional new variable. If you do that, let's think about it. When S1 equals to 0, when S1 equals to 0, this equation right here equals to 3, right? If this is 0. Are you watching? Are you looking at me? Everyone, important. Hey guys in the back. Students in the back. Hello. Hello. Important. Okay. If this is 0, then the left equals to 3. So when this is 0, this is that's equivalent to the equal sign here. So when this is positive, this part will be smaller than 3. So when S1 is positive, it will cover the smaller sign. So when you rewrite this as this, they are equivalent. Okay, so pay attention to this part. Otherwise, in the future, you don't know what to do. Okay? So when you do this, this new equation will satisfy general format, because linear format, equal sign, some positive value on the right. Okay, so this is this is one way. Actually, I think a good way to convert inequality to equality. So when you see this, use add select variable on the left. And there is another situation. So the other situation is, this time, it's larger than or equals to. So this time you cannot add the select variable. You have to minus another kind of variable. this time minus T1. And T1 must be positive. So T1 is called surplus variable. Okay. So let's look at T1. When T1 equals to 0, that covers the equal sign here. When T1 is positive, this chunk is greater than 3. So when T1 is positive, that covers the larger than sign. So this shows the lower equation is equivalent to the upper equation. Okay? So the only difference between this one and this one is the direction of the sign. This is smaller than, this is larger than. Okay? And the goal at the end, you need positive value on the right hand side. So if one day, let me show you another example. If one day you are handling negative value on the right, what do? You convert it to positive first. So you multiply -1 to the entire equation. So the sign switches to larger than or equals to. So this one will be the second kind. So in this second kind, you will introduce surplus variable. Okay? But you may question, hey, how about coefficient in front of x? Can it be negative? Actually, yes. If you look at the general formulation, there are no rules about small a. So the big A matrix can have coefficients that is negative. There are no rules about all these coefficients inside A. Okay? So after introducing select variables and surplus variables, now you understand how you can convert inequality to equality constraints. Now, another thing I would like to talk about is number of variables and number of equations. So for linear programming, usually, do we have more number of equations or number of variables? So that's something we need to think about. So there's one case when n equals to m. So these are linear equations. If you have n unknown with m equations, that's basically exact right amount of unknown and variables. So you can solve the linear equation to get the solutions. So there is only one solution, right? Exact solution, if the solution exists. So if you have same amount of variable and number of equations, in that case you have only one solution. And of course, the rank of the matrix is m. Then it's a solvable linear system. In that case, only one solution. If the problem only has one solution, you don't need to do optimization because there is only one solution. So for LP, we don't need to handle this kind of situation when n equals to m. And how about n smaller than m? So when n smaller than m is called a situation so-called the overly constrained. So usually, when it's overly constrained, most likely there will be no solution. Too many rules. What does it mean? Let me give you one example. If I say x equals to 2 and x equals to 3, so what does that mean? One variable, two constraint. So this is n equals to 1, m equals to 2. But it's impossible. X cannot be both 2 or 3. It can only be 2 or 3. Cannot be 2 and 3, right? So these two constraints cannot be satisfied at the same time. That means you can never find the right solution. There's no solution. So in this case, n is smaller than m. It's overly constrained. So the other case, m is larger than m. In this case, is called under constraint. And in this case, you have many solutions. In the feasible space. Okay? So when you have many solutions, you have infinite number of solutions inside the feasible space. So you need optimization to find it. You need optimization to find one point inside the feasible space and claim that one is the optimal. So for this course, for optimization, we only handle the case for under constraint. Number of variable larger than number of equations. Okay? So we can only handle this. Okay? There are two general methods to solve for LP. I'm going to introduce only one. I like this one more. Okay, the other one, you can Google for it. It's also very simple. Okay, but not going to be covered in this class. So the other method that I'm not going to introduce is called the simplex method. So not covered in the class, okay? And the method I'm going to introduce here, I don't know the name. It's called, basically is the method that divide the variables into two kinds. So it's a method with so-called the basic variables and non-basic variables. don't know the exact name. If you Google for it, maybe GPT or Wikipedia has the name, but I don't have the name. Okay, so I'm going to introduce this method. Okay, so later on, I will use maybe capitalized case B to represent so-called the basic variable. And over here, I will use capitalized N to represent non-basic variables. Okay, so for among all the variables, we need to separate them into two groups. One group is basic, the other group is non-basic. Okay, now let's use one example to show you what is basic and non-basic, and then I will derive the mathematics. So let's use the example at the bottom. Okay. So let's directly take a look at one linear programming problem. And also, so let's just take a look at this problem. Before we start, we need to convert this into equality constraint problem. So how do we do that? We will introduce select variables. So right here, let me just use blue color. Anyway, red is okay. Okay. I intentionally write it in this form. And pay attention to the select variables. Here, I am adding x3, here adding x4, here adding x5. And make it equals to 7 and 3. Okay? And also,
这些是符合 OK and also 的项目。
Also, with the additional x3, x4, and 5, in fact, I am adding 0 times x3 here, 0 times x4 here, 0 times x5 here. So they exist in the objective function, but only with 0 coefficient in the front. Okay? And also, they must be positive. So additional rules. They are positive. So originally, this was the original problem. Right? This is the original problem. And whatever that is written in red and green are the additional treatment. As these are slack variables. They are artificial variables that I introduced. In the original problem, there are no x3, x4, and x5. at the end, when we find the optimal of this new problem, when it's finished, we don't care about x3, 4, and 5 anymore. x3, 4, and 5 are here just to make this general format to be written as a standard format of linear programming. The purpose is only for linear programming. Okay? Now, oh, by the way, in the exam, you need to solve by hand. So this is the chance for you to just understand what's going on. Okay, so now I can write it in a vector and matrix form. Rewrite the whole thing in vector and matrix form. So I would have these. So over here, actually, you have x1, x5. I want to write down the whole vector. So I have to. Okay, here. Two, 7, 3. Okay. So after writing down the new format in this vector and matrix form, it looks like this. Okay. So I'm going to tell you that we are going to group the variables separate them into two groups. And I'm going to tell you how we are going to group them. For the first two of them, x1 and x5, they are the first group. x3, 4, and 5, they are the second group. And for the first group, I'm gonna call it the non-basic variable. And this one is basic. I'm gonna group it in this way. So what's the trick of grouping? So the rule or the strategy of grouping is that the number of basic variables should equals to number of constraints. Number of equality constraints. Okay, so in this case, we do have 3 by 5 problem, right? So this means our m equals to 3, n equals to 5. So number of equality constraints means m equals to 3. So the number of basic variables should be 3. When you do the grouping, choose 3 of them. Okay? And the way I design the problem, I always choose the last 3. That's an easy start for linear programming. Sorry. Okay, so once we do that, once we separate them, we are now going to do the same thing for their corresponding coefficients. So, because we group separate x into two groups, we're going to do the same thing to C and A, based on the same type of grouping. Okay, so here, this would be the A matrix, but the basic part. And here would be the A matrix, but the non-basic part. And right here, this would be the C vector, non-basic part, and this would be the C vector, basic part. But please be aware, when we write the objective function in this particular form, the C vector is supposed to be a vertical vector, but we actually transpose it. So don't forget about the transpose sign. T represents transpose. Okay, so what we are doing right here actually is this. And for the B, B remains the same. Okay. So what we're doing is actually like this. Okay. So why do we do this? Let's try to expand these vectors and matrices and try to find a reason why we do this. Okay, so let's expand. So this is gonna be transpose xn plus cb transpose xb. And this can be written as an xn plus ab xb. Okay, right? So there's another rule for this separation. For the non-basic variable, initially, all non-basic variables are 0. So there's a rule. All the non-basic variables at the beginning, they are 0. Okay. If they are 0, what's gonna happen? So since xn equals to 0, they are 0. So you can have ab xb equals to small b, and you can then solve for xb equals to ab inverse B, right? So this is like a initial feasible design. So at the beginning, all of your non-basic variables are 0, and your basic variables has some values. Non-zero. Basic variables are non-zero. So you can solve for it. So in this case, you can easily see, because x1 and x2 are 0, so these coefficients multiply a lot of 0 equals to, doesn't contribute to anything, equals to 0. So all you need to pay attention to is this matrix multiplying the basic variables equals to the coefficient on the right, small b. Since I chose this one as our initial AB. AB now is identity matrix. So identity matrix times x3, x4, and x5 equals to x3, x4, x5. So x3, 4, and 5 equals to 2, 7, and 3. So initially, you already know the solution of the initial setup equals to 0, 0, 2, 7, 3. That's the initial design point. So 0, 0, 2, 7, 3 will satisfy the constraint. It's a feasible design, but not optimal. Maybe not, usually not. But it's a feasible design. Okay? So let me write it down. In this particular case, x1 and x2 equals to 0. And you can solve for this. Equals to 2, 7, and 3. So x3 equals to 2, x4 equals to 7, x5 equals to 3. So this will be a feasible design. So linear programming has to start with a feasible design. Okay? Now continue. Okay? So, but in general, xb equals to what? In general, xb equals to b vector minus an xn with ab inverse in the front, right? If you derive from that general equation, that's how you can evaluate xb. Let's expand xb. So xb equals to ab inverse small b minus ab inverse an xn. Okay? That's another expression of xb. How about we plug in xb into our objective function? So plug in to objective function. Okay, what's gonna happen? So the objective function would equals to the cn transpose xn plus cb transpose multiplying xb. So copy the whole thing. Copy this, paste here. Okay, so that would be how the objective function would look like if you observe in this way. So let's expand the terms again. Okay, so this is how it looks like when you expand the whole thing. And let's pay attention to one term, which is xn right here. You can see that there are two terms ends with xn. Let's put them together. So right here, cn transpose minus cb transpose ab inverse an, and then xn here plus cb transpose ab inverse and small b. Okay, now let's observe what this equation is about. C comes from the coefficient of objective function. A comes from the coefficient of the constraints. Small b comes from the right-hand side of the constraints. So this chunk are just a bunch of constant values. This chunk is another chunk of constant values. So this whole thing basically is a linear equation. It's like ax plus b, right? So here, they are constant. This is constant, okay? So when you observe the objective function in this way, because these are constant values, you cannot change the constant anymore. So no matter what you do, when you make the decision of basic and non-basic, this constant is the same constant all the time. But when you decide who are basic, who are non-basic, there will be a bunch of constant in front of the non-basic. And remember, what's the value of non-basic at the beginning? It's 0, right? Non-basic are zeros. And in linear programming, all the x must be positive, right? So the non-basic variables are 0. If we try to increase one of the non-basic variables, if I increase it, it will satisfy the rule of LP. But when you increase it, if you increase one of xn from 0 to some positive value, is your objective function going to drop? What's the scenario for function value dropping if you increase one of the non-basic? So you would like this part to be negative. The corresponding coefficient in this chunk, you want that corresponding value to be negative. So when you increase one of xn from 0 to a number, because of the negative coefficient, that combination will be a negative value, and that will decrease your objective function. So you can minimize. Okay? So let me show you what's happening. So if I use the example that we had earlier, if I copy these, actually I need to copy these. Okay, so if I use this one as an example, you will understand this better. So this will be my non-basic part. This is my basic part. This is non-basic. This is basic. So if I try to compute whatever this chunk says, let me try to compute it. So in this particular case, Cn transpose minus Cb transpose AB inverse AN. This gives me -1, -2 minus CB is 0, 0, 0. AB is 1, 1, 1. But inverse AN is -2, -1, 1, 1, 2, 0. Right? So from here you can easily see the end, it's a -1 and -2. Okay? So over here you realize your objective function actually is -1, -2 times your non-basic, which is x1 and x2, plus some coefficient in the end. We don't care right now. Okay, but initially, at the beginning, they are 0 initially. Right? So if I try to add some value to x1 or x2, which one do I add value? I would like to add value to x2 because x2 has a coefficient of -2, which will reduce the objective function value more. Okay? So this one, this corresponding coefficient is the most negative value in this copy and paste. So we are going to pick up the most negative value in this chunk. And the index, the corresponding non-basic variable will be converted, will be increased from 0 to some positive value. That's the goal. So this implies x2 to be increased from 0 to a positive value. Okay? So in LP, if a variable is positive, not 0, it's actually basic. So this implies x2 to be swapped from non-basic group to basic group. Because in the basic group, variables are positive. In the non-basic group, they are 0. So you just pick up x2 and say, this one is going to become basic. But when we pick up a non-basic and say in the next iteration, so here, very important, in the next iteration. So in the next iteration, x2 will be a basic variable. So we will have one more basic. That means originally, that means we will have too many basic variables. Because there's one rule about the number of basic variables. It has to be equals to the number of your constraints. So we took one from the non-basic group. We took one into the basic group. So we will also take one from the basic and move it to non-basic. So one of the variables from basic will become 0. But which one? The issue is which one. So I will tell you which one. Okay? So the trick right here, if you derive this equation, this coefficient, this will be a vector of the coefficients in front of the non-basic, and you pick up the most negative one, the corresponding non-basic variable will become basic. Okay? The purpose of this, why do we do this? Why? Because when the chosen non-basic variable has a positive value, the objective function value decreases. Because of its most negative coefficient. Okay? So this is the concept. If you pick up the right one, objective function will drop. And every time you do this, the objective function will only drop. It doesn't increase. So you just need to keep on doing this until you cannot find any negative value in that main vector. So this process will be done, it will be performed once in each iteration. Okay, only once. Okay, and this process will stop when this chunk copy are all has no or sorry the doesn't have any negative coefficient. Then you found optimal. If this chunk there's no negative coefficient there, you cannot find a lower function value anymore, then stop, because you cannot find a better solution. That's the optimal. Okay? So this is the first part. The second part is how do you choose one from basic, change it to non-basic. So that part, okay, I will use this. So now we will use this as a, we need to observe this. So copy. So this is the second part. Second part has a name. Second part is called the ratio test. Okay, so here, this is your A non-basic, this is your A basic, this is your X non-basic, X basic, right? And this guy is B. So let's now take a look at this using the example we have. We know now we can, let me see how we can rewrite this as this form. Right? Okay, and when we do this, we will try to observe in which way. A, B. Let's find a way to describe this. So we will expand the AN. So your AN will look like AN1, AN, and the number would be the size of this, is actually m by n minus m. So it's actually 3. Sorry, let me write it in this way. So it's m by m minus n. What does it mean? 3 by wrong. N minus m. So 5 minus 3. So 3 by 2, right? So it's a 3 by 2 matrix. So over here, this will be let me find a way to write it. I think I can. Let me just put circles, components. So this circle represents the components. So the first one, second one, and the nth one. And here, so it's like a 1, 1, 2, 1, and m1. Here you would have a 1, 2, 1, but here would be n minus m, right? So the circle represents the components. So I am trying to write down what's inside this. What's inside the AN. So these circles are the components. And then xn, you would have like a xn1, xn over here, n minus m, right? Okay. For the rest, we just write it down. So over here, there's a specific one that has been chosen to be, because xn originally are a bunch of zeros. These are zeros, and they are some numbers we don't care because originally they are zeros. But in the previous step, one of the xn will be chosen. And it will swap to the basic group. Okay, these are not basic group, but one of it. So let's say the jth. Do I use jth? Yes, jth component or jth. Yeah. Jth non-basic variables. Being chosen earlier. Okay, so right here, there will be, let's say this one is the jth. Let's say this is the jth column. Okay? Only the jth column is important because only the jth will become non-basic. Only the jth coefficient will be multiplying with the chosen one, which will become non-basic. The rest remains 0. Okay? So we can now we can say this is x n jth. X n jth. Okay? The jth one. So, and here we can say this is like a matrix, but AN matrix, but every component, or I would say jth column. Let me just write it in this way. The jth column. Okay. Okay. So if we only pay attention to those, then this will become A n j times x n j plus a b x b equals to small b. Okay, now if we write it in the following form, xb equals to b small b minus a n j x n j, and over here I will have like a b inverse, right? If I do this, I shouldn't have. I'm sorry. I did a mistake. I should do the inverse then do this. Sorry about this whole thing. Sorry. I'm very wrong. Again, I'm sorry. Very sorry. Okay, so now we should convert this into the following form. We should study xb and but we study in this way. We will okay, let's do it in this way. So plus AB inverse AN times AN equals to AB inverse small b. Okay, let's study in this way. Now we are going to call this a new name, A hat. It's a matrix. And we're going to call this B hat. It's a vector. Okay? How do I know the left is a matrix, the right is a vector? We can check on the dimension. So B is n by 1. AB should be n by m. So sorry. XB is n by m, and AB is n by m. AN would be n minus m by 1. AN will be m by n minus m. Okay. So this multiply this is m by 1. This multiply this is n by 1, so equals to n by 1. And when we rewrite the whole thing in this form, AB is n by m, AN is n by n minus m. So at the end, this will be m by n minus m. Here, AB is n by m. Here is n by 1. So B is n by 1. Okay, so this is a matrix n by n minus m. B is a vector n by 1. Okay, so this is where we actually write in this way. So let's observe. XB1, we have m of them. Okay, plus we will have a hat. So a hat, this is a hat 1 1, a hat 1. Let's write a j, a hat 1 comma m minus m, a hat m and 1, a hat m and j, a hat m n minus m. Okay, and for the coefficient xn 1, xn j, xn n minus m. Okay, and on the right hand side, do I need to? Okay, we don't need to. We just write it down. We just write b hat. B. Actually, we can write b hat 1, b hat m. Okay, because we know it's m by 1. Now, as I mentioned earlier, similar to what I said, these are 0 initial. Okay, these are non-zero. These are 0. But we chose one of them, and this one will become basic. So that one will have non-zero value, positive value. So let's say this one. So let's say jth non-basic was chosen earlier. Okay? So its corresponding column, this jth column in a hat, is important because the rest is not important. The rest of the columns will multiply with 0 values in non-basic group. So the rest, we don't care at this moment. We only care about this column because this column is going to multiply with the chosen non-basic component. Okay? So when we do that, we can actually rewrite in this form. It's like this. Only right? It's actually like this. So originally, these are 0. X, B, the first basic to the last basic equals to the first B hat to the last B hat. So when I increase this, something's gonna change. Something's gonna change. So for the B hat, there are several situations. B hat can be positive, can be 0, or can be negative. Okay? So there's no rules about B hat. So let me draw a picture to show you. We can actually observe one of the above equation. So what do I mean? Let's say I observe the kth one, okay, plus, so if that's the kth one, then k j times x and j equals to bk. So if I make a drawing like this is x and j, and this is b xbk. So initially, this is a value of bk. So initially, x and j is 0. So initially, xbk equals to b hat k. So let's say that's three situations. One situation is like this, the other situation is like this, another situation is like this. Okay? So there are three situations. So if the line is horizontal, means a, k, j equals to 0. And this is the positive case. And hold on. Negative. Negative case and positive case. So when I increase the value, let me draw a line. So by increasing x and j from 0. Earlier we said we want to increase x and j. It was originally 0. Now when we increase, because we have to satisfy this linear equation, there could be three situations. The coefficient right here could be 0, positive or negative. If it's 0, when I increase this, this will be the value of xbk remains the same, because if this is 0, if I keep on increasing, it doesn't change anything to the equation. xbk still is b hat k. If xkj is a negative value, if it's negative, so original is 0. Now when I increase, because it's negative, so this is a negative value right here. I'm wrong. I should, this is, the case right here is positive, sorry. So here is positive. here is positive, here is negative. Okay? Choose smallest positive. Hold on. Am I right? If this is positive, this will drop. I was right. I was right. Yep. So if this is negative, when this is 0 increasing to a positive value, so this is negative, then xbk will become greater than b hat k. So you can see the value of xbk will increase. So when in the case of negative coefficient, this will happen. So when this happens, what do we want? We said earlier, when we choose one of the non-basic, we want it to become basic. So we are looking for another variable which was basic, and it needs to become non-basic later on. So if we pick up the coefficient with negative, with this particular equation, the situation, xbk cannot become 0. So we have to choose this particular case, the positive. So we want to choose xkj to be positive. So when xnj increases from 0, xbk reduces from b hat k to 0. Right? If you choose positive coefficient, then when you increase like this up to here, the value of xbk will drop to 0. Okay? But there will be some scenario. So if we choose the positive coefficients, so there will be some scenario, another situation where there are more than one positive if there are more than one inside this vector. How about more than one positive? Okay, so that's why there's something called ratio test. So the scenario looks like this. This is originally bk, and this is xnj, okay? And there will be a scenario like this, another one like this, okay? So this case, the bk over akj is smaller. So we need to pick up the kth component that is having the smallest positive value. So from here, we need we need to do the ratio test. So-called need to do ratio test. So what's the ratio test? So it's a B1 over A1J BM over AMJ. And among this, choose the smallest positive one. Okay? So let's say inside one of it, let's say Kth is having the smallest positive value of BK over AKJ. Why do we do that? Because why do we choose the smallest one? Because we only need one corresponding basic variable to reduce to 0. So 2 lines means there are 2 basic variables that can become 0. So when you increase the value of non-basic, the jth one from 0, when you increase up to here, this corresponding variable is already dropping from this value to 0. So this one is already, that particular basic is already 0. If you keep on increasing this non-basic, the other basic will become 0 as well, but the first one will become negative. We don't allow negative basic. We don't allow negative variable. So we need to know which one is going to drop its value to 0, the earliest. So that one is the kth that has the smallest positive value of this ratio. So that's why it's called the ratio test. Okay, now let's use the example to understand what's going on. So earlier right here we pick up this one, x2. x2 will become basic. Okay, so x2. So let's use this as an example. We need to compute for right here. We need to compute for what? This AB inverse AN equals to what? And also AB inverse B. This is your A hat. This is your B hat, right? So your AB inverse will be 1, 1, 1. AN will be negative 1, 1, 1, 2, 0. Okay, so this will be negative 2, negative 1, 1, 1, 2, 0. Right here, your B is 273. So it's still 273. Okay. So if you try to perform ratio test, this is what's happening. And because earlier we said the second non-basic is chosen, so we only care about the second row of a hat. So this will be the second row, second column. Sorry, second column. Okay, so second is 1, 2, and 0. So ratio test. You will have all the B hat divided by the ratio in the A hat second row, second column. So that will be 1, 2, and 0. So this is 2, this is 3.5, this is infinity. Okay? So this is the smallest positive one. Right? So the first one inside the basic is chosen. So first one in basic is chosen. Okay? So to sum up, what happened? We did a bunch of things. What happened? Let me summarize again for you. That's actually one iteration. So let me summarize what happened. Okay? So we have initially there's a problem like this. Okay. Initially, you have a problem like this, and then we did this calculation. The calculation is where? Here. We did this. Actually, when we summarize, we don't need to say this. Okay, so we will say, okay, this will be the most negative one. So second non-basic chosen. So which one is the second non-basic? Which is x2. That's all you need to do. And then what we did next was we compute for these. This is the come on. No. So next week did this. Okay, we have to compute for A hat and B hat, and we need to recognize, because you chose the second non-basic, so the second row column of A hat is to be investigated, and you do the ratio test. Ratio test basically is over here, the ratio hat is using B hat over A hat, but the jth column. Okay? The jth column, and basically this is the j equals to the second one, the second index. Okay, so here you will pick up the second column. Okay, so that's why then you did the ratio test, and you realize you will do this, delete. So because the first coefficient of the ratio test shows the smallest positive value, so the first one in basic is chosen. So what does that mean? That means the first basic being chosen. What is the first basic? Basic is 3, 4, and 5. The first basic is S3. So why do we do this again? If you choose X2 in the first part, the X2 will be converted from non-basic to basic. And for the ratio test, X3 is being chosen, and it will be converted from basic to non-basic. Okay? So whatever you're doing right here in this particular page is trying to pick up one basic, one non-basic, and then swap their role for the next iteration. You will keep on doing this until you cannot find any basic to be swapped, then converged. So you might feel weird. How come this works? Okay, so I will show you by some graphics, then you will understand. So right here, if I use this particular example and draw the figure, as I mentioned earlier. So now we already decide to increase X2. And let's take a look at all the X3, 4, and 5. So one of it is 2, the other one is 5, another one is 7. So this was X3, this was X4, this was X5. Okay, and as I mentioned earlier, the ratio here actually represents actually some kind of slope. So so if you try to formulate this equation right here, you will see more obvious this particular equation. Because right here, you actually have X3, X4, and X5 plus 1, 2, and 0 times X2 equals to 2, 7, and 3. This was what happened. So if you increase X2 from 0 to 2, x3 become 1, right? So that line actually is here. And if you take a look at the second equation, x2 has to increase to 3.5, then x4 becomes 0. So around here, 3.5 and 7, right? And no matter how much you increase x2, x5 remains 3. So those three equations can be drawn in this way. So if I increase x2 from 0 to 2, x3 already dropped from 2 to 0. I cannot increase x2 anymore because x3 will become negative. So that's why in the next iteration, x2 will become non-zero, but x3 become 0. So their role swapped. Okay, so that's the idea. So if I swap their role, what's happening is you can then draw this picture. Oh, sorry. So that's next iteration. So was in the previous iteration, these were basic, these were non-basic. Now, after swapping, x2 become basic. So x3 become non-basic. The rest remains the same. So in this new iteration, this column and this column, they are non-basic. And this column and these two columns, they are basic. So right here, this is 0, this is 0, and this one non-zero. The other two non-zero. Okay? So you will keep on doing this until you cannot find any more solution. So I have done it in my notes, so I will just quickly show you how it's done. We need to perform this. Copy. So when you try to solve it in the exam, just do this. So which one is CN? Which one is CB? Which one is AB? The pink one. So 1, 2, 0, 0, 1, 0, 0, 0, 1. Inverse. What is AN? -2, -1, 1, 1, 0, 0. So if I give you a problem with similar amount of equations, you need to do a 3x3 inverse in the exam. So I will give you an equation to help you if you forget how to do it. I will give you an equation to solve for inverse. So if you solve for this, at the end, you will end up with -5 and 2. So this is the most negative one, and it represents the first non-basic. Right now is x1. So x1 is to be swapped to basic in the next iteration. Okay? So you then need to calculate for this. Sorry. You need to calculate for this. Copy. Paste. So B inverse AN, so basically it's these guys. Copy, paste, paste. Delete. Then 273. You still need to compute for these, and I have the result already. It's gonna look like this, and here it's gonna look like 233. So because in this over here we choose the first one, which is the most negative one. So in A hat, the first column will be chosen. So this column will be chosen. So using these to do ratio test, so the coefficient will be 2, 3, and 3 divided by -2, 3, and 1, ends up with -1, 1, and 3. So this would be the smallest positive second one. So what is second one? The second basic. The second basic is x4. So these are all you need to write down in one iteration. So just move on to the next iteration. In the next iteration, I'm going to be even more lazier. I'm going to erase, just stop writing down all the x. Okay? So it's okay in the exam if you just give me this. That's fine. So here this was in the first iteration. This one in the second iteration. How about now? So let me erase the circles. So I need to swap x1 to the other side. So this become B. x4 swapped, so they become N. The rest remain the same. So this will be my basic. And this will be my non-basic. Okay, and do the same thing again. All these. I'm gonna copy and paste. And this time I'm being even more lazier. I'm just telling you what I got. Okay. So B, B, N, and B, yeah. The result would be -1.33 and 1.67. So over here, if you do that, so right here, this one is the most negative. So the first non-basic to be chosen Which one is the first non-basic? S3. To be swapped. And if you do the calculation for these, you will end up with negative 0.7. Okay. One, 4, and 2. And because earlier the first component of the coefficient is being chosen, so here the first column is going to be used for ratio test. So ratio test. So at the end, negative, we don't care. So this one is the smallest positive. Because the other two are negative. We don't even need to calculate. So this one will be the third one. Third basic, which is x5. Okay? So next iteration will be x5, x3 swap to b, and then x5 swap to n. The rest remains the same. And then do it again. Until I can tell you the next time. So next time, this will become all positive. So converged. Because they are all positive. Okay? So what does it mean? That means this is our solution. BBBNN is our solution. Wait, what does BBBNN mean? So BBBNN means right here. Copy. Erase. Erase. And erase. So BBB are x1, x2, and x3. Okay? I should write down the complete things. BBB represent XB, x1, x2, and x3. Just solve for this equation, then you can get x1 to x3 and x4 and x5, they are 0. Okay? And if you solve for this at the end, x1, x2, x3 equals to 3, 5, 3. If you truly try to solve it. 3, 5, 3. Okay? And let me make a drawing of this. Here is x1, here is x2, and here should be around here. Around here. And the slope is like this, like this. 3 and 5, or 3 and 5. So probably here. And the other one will be somewhere here. And like this. Okay. So in fact, this is the problem. This is the original problem. If I show you original problem, copy, and paste. This is the original problem. So this is G3. So this is a G1, G2, G3. Okay? So when I draw this hash, that means on the right is infeasible, on the left is okay. And the other one, if I plug in 0, so this will be G2. This should be G1. Okay, and it's like this. So in fact, the feasible space is here. Okay, and what does the objective function look like? Objective function, the contour of the objective function is like this. So here is decreasing. Okay, that's the objective function. So if you try to solve it by hand, and every time try to figure out what's the value of x1 and x2, you will realize actually when we first initiate the problem, we start with 0, 0. So this was our initial. And actually, when we did the first iteration, this is where the solution was, 0 and 2. And then we actually move up to here, 1 and 4. And then we move up to here, 3 and 5. And we can no longer find the solution. Okay? So I would like to give you one simple homework. Okay? Please solve same problem by hand and try to make same drawing on the left. Okay? So in every iteration, solve for your x1 and x2 so that you can observe how x1 and x2 really change from 0, 0 and gradually move along the edge and find the intersection, stop, and move along another direction and stop until it can no longer find the solution. Okay? So let's have a homework for this. Because in the exam, linear programming will be the most part. So I want you to truly practice by hand. Okay? Just exact same problem. You can even go to my previous lecture video. I did this problem multiple times already. So you can follow exactly what I did. You can try it by yourself. Okay? So that's it for today. I still have some time. Do you have any questions? Does anyone know why linear programming doesn't go along this direction? Let's think about it. Anybody? Okay. So if you take a look at what happened at the very beginning, we try to derive this equation. We just rewrite the objective function and it ends up with some coefficient times the non-basic plus some coefficient. So the coefficient right here actually represents some information about the slope. Okay, so right here we said we have to pick up the most negative one so that when this increase, this will drop faster. So pay attention to this part, and if you take a look at the drawing right here. So the slope or the contour of the objective function actually is steeper along this direction. So if you move along this direction, if you take one step, function value drops more. If you go right, if you move by 1 unit, function value doesn't drop as many. So here is the direction that function value drops more, faster. However, in this particular case, the solver doesn't know there are so many intersections right here. So it doesn't know that if the process go along this way, you need 1, 2, 3 iterations. But if you actually go toward right, you actually can. If you go toward right, you will end up with 2 iterations. Then get the solution. The solver doesn't know what's going to happen at the end. It's not a graphical approach. It's not like, okay, let's take a look at the map. Okay, boom, let's go this way. Mathematically, it's a numerical approach. It doesn't know how many constraint functions are there. Okay? So linear programming is a method that tries to start from one corner and tries to move along the linear surface and try to find the intersection point and then stop and then keep on doing this until it cannot find any more solutions. So it doesn't penetrate through the space. It moves along the edge. So imagine you are solving a higher dimensional problem. The linear constraints will form a hyperdimensional geometry. And then every 2 linear constraints will have an edge. So your design point will stay on one side of the edge. If the objective function will drop along that particular direction, so your solution process will move along that edge until it's stopped by an intersection point. Then do the same thing again. So it's an edge moving strategy for linear programming. Okay, so how about nonlinear problems? You can use first order Taylor expansion. To linearize all the equations. So if one day you see nonlinear problems, first, linearize. Second, convert to standard format. Because maybe sometimes you have inequality constraints. So convert to standard format. Then linear programming. So what's gonna happen if you get the optimal solution of bilinear programming? Is that the solution of your original problem? Actually, no. Because right here you did approximation. So here is a linear approximation. Right? So starting from nonlinear, you make Taylor expansion. That's a kind of approximation. You linearize the problem. You convert to LP format, solve it by LP. That solution is only the solution for your linear problem. So if you go back to here and perform another round of approximation and go through the process again and again and again and stop if converged. If the process will just stop when converged. If you do this multiple times and then the solution is the same one, same as the previous linear programming, then you can stop, right? If you do this, this is called sequential linear programming. So-called the SLP. Okay? So if you know how to do SLP, you can already solve a lot of problems. Linearize LP, do it again, linearize LP, repeat until converge. Okay, so in your project, if you want to try some kind of sequential approach, this is the process. Okay? Now, I think we should do a roll call. So, 一拳 is Zhen Xuan, not here. Okay. You are, forget your name. Giovanna? Giuseppe. Okay, Giuseppe. Okay. 志文有 Okay. 易安 Okay. 子炫秋明 Yes. 博欢 Anna Yes. 陈琦 Okay. 安佑 Okay. 林志显玉 Okay. 博元 Okay. Anyone missing? So the number of students show up become less. So maybe later on send a message to the group, remind them to come to the class. Okay. And also remind everyone we have a homework. Okay. Any questions? We have a homework. I know earlier I mentioned there's no homework, so I will give the homework some points. How about 3 points? Like an extra point. Okay, so homework. I will show you what I mean. So earlier I said there's no homework. So here I will just for linear programming, I I have a homework, so let's say 3 points. So in total, that would be. So the max you can get is 1 of 3. 3 extra points. Okay. So please, I think linear programming requires a lot of hand exercise. So please practice. Okay? Any questions? We will have a proposal on May, so please make sure you have discussion with your teammates. Okay? Your teammates are here. I worry about foreign students. Do you know them? You don't know. Okay. So, Tajiro can like send message to them, remind them to come to class. Yeah. Otherwise, their teammate will worry. Okay. Yeah, that's why we need to remind them. Yeah, if they plan to drop or not care about the course, at least I need to release them from their group and regroup, right? Yeah, so please double check what happened. Okay, thank you. That's it for today.